Hey, good morning or afternoon or whenever you're watching this. We're starting a new section called Electrical Systems. Okay, looking at types of circuits, electric power, and electricity in the home. So, in this section, we'll describe the differences between series and parallel circuits, describe short circuits, fuses, circuit breakers, calculating electric power, how we figure out our electric bills, difference between AC and DC circuits, um, and just how electricity gets to your home. So we're starting off with series and parallel. It says, what is the difference between these two circuits? So if we look at these two circuits, the one on the left is what we consider to be a parallel circuit, and the one on the right is a series circuit. Okay. So the current in a parallel circuit on the left, the current can flow more than one path. So it has different choices of which direction that current can flow. Okay, where a series circuit, the current can only flow through one path. Okay, so if you're looking at the one on the left, the parallel, okay, it's going to flow through, and at this point, when it gets to a junction, as you can see in my arrow here, it has a choice. It can either go straight through or it can go right through there, but it can't do both. Okay, same with this junction, and then up here, the last piece it can go through. So really, each electron that is moving its way through, or each charge that's moving its way through, can go through only one of the different branches of that circuit. Where on this side, you have three different resistors, okay? And whatever charge is going through here has to go through all three. It doesn't have a choice. There's no branches, doesn't have any other paths. It's the only path, okay? So I like to think of it like toll booths, okay? Right now, our toll booths, way they're lined up is they're kind of like in a parallel circuit, okay? When you have traffic flowing through the highway and you get to a toll booth, you have a choice of which lanes to go into, okay? Right now, because of the epidemic that we're in, or the pandemic that we're in, we have everything's easy pass. So everybody's got to go through easy pass, and you have a choice of all those different lanes. But if they were lined up in a series, that would mean that everybody has to go through every single line. So if you had your easy pass, your cash lane, your change only lane, whatever, everybody would have to go through that. Now think about traffic, okay? Which one would be better? Well, obviously, if you want to keep the traffic down, the parallel way would be better. It would allow for the traffic to flow easier because now when they get up to the toll booths, each car has a choice and it spreads them out. Okay. Where if it was one after another, that means that you would have to wait for everybody to get through each part of the toll booth. Okay. So it would slow things down. Does the same thing in a circuit. Okay. The current is going to slow down the more resistance there is when there is a series circuit. Okay, so if I added one more to this, okay, if I added one more resistor to this, it would slow it down even more. And if I added 10 more, it would slow down even more. Okay, and then on the parallel side, it does the exact opposite. If I add one more branch, now you got more choice. You got another choice to make. It would actually ease up on the traffic. It would allow it to flow even greater. Okay, so the current would increase every time I added one more branch to this parallel circuit. So to figure out the type of circuit it is, it says place your finger. I'll put the cursor on here. Actually, I think I can actually make it a. Let me see if I can pick a different cursor. Oh, there we go. So now you can see my little pointer thing. Okay. So it says place your finger on the positive end of the battery and trace the path along the wires. If you pass through each device, it is a series circuit. If not, it is parallel. So this is my positive side of the battery. I'm going to flow through here as I come across. Okay. At this point, I have a choice. I can only go through. Remember, all currents are going to flow from positive to negative. So even if I go to the next branch, okay, I'm going to flow. It's a one-way path here. So it's not like I can get to this branch down at the bottom and move back through here. That won't happen, okay? Everything's going to move. It's a one-way street back to the negative side of the battery, okay? Same with the last one. I can only go through that last one. I cannot go through more than just one resistor there, or one, in this case, one branch of the circuit. But looking at the series, now I come through and across, and I have no choice. I have to go through each of these resistors to get back to the negative side. There is no other way. Okay, so that's how we know it's a series circuit, because it's got to go through all of the resistors. Okay. There we go. Okay, so with series circuits, that's what we're going to look at mostly today. Okay, series circuits, there's only one path for the electric current to flow. Current must travel through all devices in the circuit. If one device breaks, the circuit is open and current stops flowing. So if you look at this, if these resistors, if this was a light bulb, okay, and the old light bulbs, they used to have little wires that kind of look like this, look like little spirals, okay. If one of those broke, it would not allow the electricity to flow through. So it would be an open circuit and none of the lights would work. Okay, so even if you had another light bulb on that same circuit, that light bulb wouldn't work because no electricity would be able to get to it. This is how the old holiday Christmas lights would work. Okay, if you had lights on the tree or outside or something like that, and one light bulb went out, usually the entire thing would go out. Nowadays, they fixed that a little bit so that now usually only these sections go out instead of the entire thing. So usually a small section of light bulbs are somewhat in series, and then the rest are kind of parallel to that. And even better ones would actually allow it to, even if one light bulb went out, it would still work. Connecting lights to a switch. If you connect lights to a switch, obviously if you open up the switch, the lights would go out. So, currents in series. Since the current can only travel one path, the amount of current in the series circuit will be the same at every point. Okay? To calculate the current in a series circuit, use the total resistance and the total voltage. Okay? So, just like the idea of the toll booths, okay, if I added one more toll booth and they were in series to each other, one after another, it would slow everybody down because they're all going through that same thing. Same idea with like speed bumps. Okay, if I put 10 speed bumps in a row, it's going to slow down all the traffic that's trying to get through those speed bumps. Not just one car, not just the car that's going through the first or the last one. It's going to slow everybody down. Okay, that's how it works with series. Okay, so each object can have a different resistance. So just like here, this has 20 ohms of resistance. This has 40 ohms of resistance. Okay, resistances are added together to get the total resistance of the circuit. So since every charge is going to go through each of these, when we want to find the total resistance, we just add those together. So if this one's 20 and this one's 40, we add them together. 40 plus 20 gives us 60. Okay. And if there was a third one, there'd be another number here. Okay, so R1 plus R2 plus ... That ... means they're just going to keep adding to each other over and over again. If there was 10 resistors, we'd add all 10 of them up. Okay, so just like we said, in this case, it was 20 ohms plus 40 ohms, gave us 60 ohms of resistance. Voltage. Each device uses some of the voltage provided by the battery. Okay? So voltage drops the amount of the voltage used by a device. So when you have a device, let's say you have like an outlet, 120 volts. Okay, that means that from one end of the outlet to the other end of the outlet, the voltage has to drop the full 120. But in a series circuit, it's only going to drop by that 120 little bit by little bit across each of the resistors. So if you add all the voltage drops from all the devices in the circuit, it will equal the total voltage of the battery. So again, if you're coming out of that outlet with 120 volts, it might drop 60 volts across one device and then another 60 across the other device to add up to a total of 120. Okay. If it was a battery, let's say a 9-volt battery, maybe it drops 5 volts over one and 4 volts over another. And that would get you your 9. Okay, but no matter what, it's got to go from whatever the total voltage is, 120 or 9, whatever it is. down to 0 before it gets to the other side of the battery or outlet. Okay. So we just add the voltages up to get our total voltage. So the voltage drop across each of the devices to get our total. Okay. Now we're going to look at some example problems. Okay, so let's look at the first example. Okay, it says find the total resistance of the circuit, find the current for that circuit, and then in the next one we'll find the voltage drop across each of the device and check the results. So to find the total resistance, like we said before, okay, oops, let me try to use this thing here. Okay, right spot. Okay, there we go. So to find the total resistance, okay, oops. Oh, I gotta get a pen. There we go. Okay, so we'll say RT, R total, okay, is equal to R1 plus R2 plus, now in the formula we saw dot, 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 but in this case there are 3 resistors. If we look, we've got one resistor here, okay, we got another resistor here, and we have another resistor here. Oops, I just blocked that color there. Let me just get rid of that. Okay, there we go. Okay, so that's our 3 different resistors. Okay, so in this case we're going to have a third R3 as well. Okay, so when we add these up, we've got 1 ohm. Okay, it doesn't matter what order we put these in or anything. Plus 3 ohms plus 2 ohms. Okay, we add that up, 1 plus 3 plus 2, and we get a total resistance of 6. Okay, so that's our total resistance. So then it says, well, what's the total current? Okay, so we know that our formula says, oops, click that button. It says V. Oops, come on. Let me redo that. Okay, so V is going to be equal to I times R. Okay, in this case, since we're talking about the total voltage and the total resistance, we're going to say RT and we're going to say VT. Okay, so to find the current that goes through, we're going to plug our numbers in. So our total voltage in this case, we can see it up here in the problem itself, is 12 volts. So we can say 12 volts, okay, equals I times our total resistance, which was 6. So to find the current, we're just going to divide both sides by our resistance. Okay, that cancels out our 6's on this side here, so we get 12 divided by 6. So what our total current, oops, sorry about that. Okay, our total current, this thing is so hard to write with sometimes. Okay, I equals 2. And the unit for current is amps. Okay, so then we're going to look at the next one, the second part of the problem. Okay. Oops. So I go to my next page. There we go. Okay, so now we want to find the voltage drop across each device and check the results. Okay, so to find the voltage drop across each one, okay, we're going to say V1 equals I times R. Now we said the current, once we find the current in 1, we've got the current for the entire thing. So our total current in this case across each of the resistors is going to be that 2 amps that we just found in the previous problem. Okay, so we're going to look at the voltage drop across the first resistor. Okay, so the current stays at 2. Okay, the first resistor, we'll call this one our R1, okay, is 1 ohm. So we're going to say 2 times our R, which is 1. So we get a total voltage drop across that first resistor as being 2 times 1, which is 2 volts. Okay. Then we look at the second one, V2. We're going to take our current times our second resistor. So we've got 2 amps times our second resistor, which is 3 ohms. And we get 2 times 3, which is 6 volts. Okay. And then we take our last one, V3 equals I times R3. So again, 2 amps times our R3, which is 2. And 2 times 2 gives us 4 volts. Okay. So if you remember from from the section, it says to get the total voltage across the entire thing, it should drop across each of the resistors. So in this case, we've got 2 volts dropping across resistor 1. We've got 6 volts dropping across resistor 2. And then we have 4 volts dropping across resistor 3. So when you add them up, our V total is going to be equal to each of the V's added together. So 2 plus 6 plus 4, and that gives us a total of 12 volts, which is our voltage of the battery. And that's it.